Well, there are some problems. Now let's first again look at a specific feature of deductivism that seems to make it especially attractive, and that is that it's something very, very abstract now when you read it here. Deductivism seems to successfully exploit what is called the asymmetry between verification and falsification of general hypotheses. Okay, general hypothesis is clear. We talked about that from the very beginning. We need them in science. And then there seems to be something which is an asymmetry, meaning that the two things are not treated equally, namely between verification and falsification. Verification of a general hypothesis is showing that the general hypothesis is true. Falsification is showing that the general hypothesis is false. And the statement is there is an asymmetry, right? It's somewhat different between falsifying and verifying an hypothesis. So what does this asymmetry consist in? It consists in pressing this button and nothing happens? No. Here we are. It consists in the following. The verification of a general hypothesis, a definitive proof of its truth, is impossible. Right? Verification means show that it is true, really show, demonstrate it, right? And that's in the empirical sciences, unfortunately, not possible because we have infinitely many cases, and we cannot run through infinitely many cases in finite time, right? Unless the time shrinks faster than the expansion, but that's a mathematical trick that doesn't work, right? So it is not possible to verify a general hypothesis because infinitely many tests would be necessary, and that we can't perform. That was the problem of induction. But the definitive falsification of a general empirical hypothesis seems possible. Why? Because you need a single fact that contradicts the hypothesis. One single case is enough. Now take this very simple example of all swans are white, right? If you want to verify it, you've got to run through all the swans in the universe, right? Look at it. Are you white? Yes, thank you. Are you white? Yes, thank you. And go through all the swans in the universe, not only today, but also in the future, okay? That's a very long story, even for a master's thesis. That's too much work, okay? But if you want to falsify the hypothesis, it means you have to find one single swan. So what do? You buy a one-way ticket to Australia, right? Go there, look at that black swan and says, here you are, right? Hypothesis falsified. By one example, right? And then you telephone back and save the money for the return flight, okay? Thank you. Okay, so you see the point, right? That's the asymmetry. For the verification, you need infinitely many cases, and for the falsification, you need only one. And that is what deductivism exploits. Deductivism says, well, that's the trick. We don't even try to verify general hypotheses because we need infinitely many cases. That's not possible to do. But what we can do is we can definitively falsify hypotheses by having one counterexample, right? By one single case. And that's the asymmetry, what I describe here. And therefore, deductivism is so attractive because it tells you you can avoid this damn problem of inductivism, which tells you, yes, to have more and more and more and more and more data, and it never ends, right? And you can never definitively prove it, but what you can do, you can definitively disprove it. And therefore, you should turn around in science from deductivism away from the idea that you have to have positive evidence, showing the truth or confirming or making it plausible that a hypothesis is true. No, says deductivism, that doesn't work. You've got to do the opposite. You've got to try to show that the hypothesis is false, because that you can definitively establish. Right? That's the idea. So what deductivism does is, and now possibly you understand the sentence a little better, because it exploits this asymmetry. It lives from this asymmetry by telling you, forget it about this verification. It's not possible, doesn't work, right? We can't do it, but here's something we can do as finite human beings. We have one counterexample, and then we can eliminate definitively a hypothesis, right? And what remains with us are hypotheses, of course, that are fallible, but we continue testing them, right? So there seems to be a very special attractive feature of deductivism, similar in attractiveness as I described to you inductivism, where the attractiveness was that we start with something that's theory-free and therefore practically certain, right? By doing theory-free observations. That looks good. You say, okay, that's nice. We start from something which is really certain, and then we build up, right? That was the attractiveness of inductivism. The attractiveness of deductivism is somewhere else because that dream of inductivism has evaporated. You know, it doesn't exist. You know, these theory-free observations, sorry, don't exist. And even if they existed, the generalization wouldn't work, really. So we've got to give that up. And deductivism says, yes, but I have shown you something else that's at least as attractive. And that is this asymmetry of falsification and verification. And therefore, we've got to turn around from verification, from a bottom-up verification to top-down falsification. That's the trick. That we exploit. And then we get a philosophy of science by which we really understand how science works. So that's the idea. And I hope this is plausible to you because I'm bringing this description here under the title of Problems of Deductivism because unfortunately things are not that simple. On closer inspection, the situation is more complicated. Look at the following situation that you really want to falsify a hypothesis, and this is something you all have heard in your scientific career already, that the falsification of a hypothesis is done by some measurement, but you must assume that the measurement is reproducible, right? What does that mean to be reproducible? Well, it means that you measure something today and you get a certain value, say you measure the whatever it is, temperature, whatever it is, and that measurement is reproducible means that you repeat, if you repeat the measurement under the same circumstances, the next day the result will be the same. So the result will be stable, right? So if you measure the weight of this little thing here, then the measurement is reproducible. You measure it, and then it's 46 grams or whatever, and then you assume, usually you assume that if you measure the same weight tomorrow, that again it will be 46 grams unless someone has removed the batteries in the meantime, who is then a very bad person because he's obstructing science, okay? All right, but we don't assume that usually that someone fiddles around with your data or your system in the meantime, and if everything goes well, then we know that measurements of stable properties, of course, are reproducible, and they must be reproducible. Now, the point is when you say I have a hypothesis here, and I falsify this hypothesis by this measurement because the hypothesis predicts something and the measurement says something else. And if that falsification is supposed to be definitive, then of course you must assume that you can reproduce the measurement. Right? If someone else repeats the measurement or you repeat the measurement the next day or in a year from now, then it must still falsify. Right? It must be the same measurement, but it must be reproducible. But that's a problem. Why is that a problem? That assumption makes use of an inductive generalization. You say, I've measured it 5 times now, or 10 times, or 100 times, and also tomorrow the same measurement, the result of the measurement will be the same. So you're inductively generalizing. Reproducibility, oh, damn it. Reproducibility. The posit of it is already inductive because you're not only saying I have reproduced it 5 times, but you mean by reproducibility that you can do that again tomorrow, the day after tomorrow, and the day after tomorrow. So in other words, in order to have that one empirical datum that is capable of really falsifying your hypothesis, isn't that, in a sense, just a single datum? Because it's that single datum with that function only if it's reproducible. And in the idea of reproducibility, there's already inductive generalization. So the problem is that we wanted to avoid, inductive generalization by saying, oh, we exploit the asymmetry between falsification and verification. But if you look at it closely, then it shows that even in falsification, beneath the surface, because you have to postulate reproducibility, there is again inductive generalization. So we didn't get rid of the problem of inductive generalization. And that's an insight that's, of course, not so nice. I mean, we started with the attractiveness of deductivism by saying, yes, it avoids the problem of induction. Wonderful. But then it turns out that you really look closely have to do with falsification, that you didn't get rid of the problem. Right? It only looks better, but it isn't really much better. And that's, of course, unpleasant, an insight. A definitive falsification is also not possible, as a definitive verification is not possible. Right? Also, a definitive falsification is not possible. So we didn't proceed very far, towards something definitive, which we believed we could. Namely, it looked as if we could definitively falsify some general hypothesis by some data that contradict it. But that doesn't work, because in order for the data to be stable meaning reproducible, you have to generalize and assume that this datum is reproducible in the future, which is nothing else but an inductive generalization. Okay? So the problem is, we try to get rid of inductivism, but inductivism creeps in through the back door, right? And we can't get rid of it. And that's, of course, somewhat disappointing, right? And that is a problem of deductivism. That wasn't seen in the very beginning of deductivism, because it looked so nicely with this asymmetry. Verify, okay, forget it, doesn't work, so we falsify, it works. But if you look closer, it has the same problem, so which we don't get rid of. Okay, that was the first problem, which again is a problem insofar as it decreases the main attractiveness, right? That what made it so attractive as a position is now undermined. And it says, oh, unfortunately, it's not that simple. But here is something else, another problem, which is in a sense even graver. It's similar to a problem that, I'm sorry, my thing doesn't work here. Let us look at this consequence of deductivism. That's now the second main problem, therefore the number 2 here, although there was no number 1 on the slide before, but this is number 2. The rule that science should never stop its attempts to critically test hypotheses leads to unintended and unpleasant results. And that is something I'm going to show you now. I mean, it looked, this is this critical spirit of science, which made it attractive to Western intellectuals at least, and of course to other scientists who entered the Western tradition in a sense, by joining this movement of modern science, which is a Western invention, of course, no doubt. But it looks so attractive, this critical attitude, but if you look a little closer, this critical attitude produces problems, unintended and unpleasant results. And I'm going to show you why. And then you perhaps say, I don't want to be a very critical scientist, or perhaps you draw other consequences. Let's see. Okay. Now suppose the following, and this is now something I already hinted at in an earlier session on inductivism. Suppose you have a hypothesis that states a specific functional dependence of a variable y on a different variable x. Right? Suppose this is your general hypothesis, this is a particular function, whatever it is, it may be a constant or whatever function it is. Suppose you have that hypothesis and you want to test this particular hypothesis. Here's a real-life example. I think I mentioned it already. You take Boyle's gas law in its in its simplest form. Temperature is constant, so P times V is a constant. Or here you've got the dependence, then P, K is a constant, is a function of V, namely 1 over V times K. Right? This is the function. This is a particular example of this one. Oh, take another example. Ohm's law, already mentioned it. Here you've got the current as a function of 2 variables, namely of the resistance, which is for a particular piece of matter a constant, and the voltage. Right? These are examples, real-life examples, that you may want to test empirically, and then you have to look at the dependence, whether this P really depends on V in this way, or whether it doesn't. Okay? Now, the problem is really this, that the test of that hypothesis does not only include that y does indeed co-vary with the variable x in the way the function f states. Right? The function f tells you, well, if you change x a little, then y will change in the following way, and that, of course, you can test. So in that particular case, if you increase the voltage, then the current should increase proportionally, right? That is what Ohm's law tells you. And the test is, of course, finding that out, whether that's true. If I change V, and then whether I, the current, will also change proportionally with a proportional constant 1 over R. So that is the test. That's, of course, a part of the test, but that's not the end of the test, right? That's certainly not the end of the test, because you have to do the following. It must also include, the test must also include the test of the assumption that y depends on the variable x only, right? That's an assumption that's in this functional dependence. And it could also depend on additional variables, u, v, w, etc., right? So testing a dependence of y and x does not only mean, if you say that's the general connection between x and y, it doesn't only depend on that. If it's worthless if there are other variables as well, right? And you must test for these other variables. Now, the list of potentially influential variables is indefinite. That's the problem. We already encountered that problem in inductivism, and it's the same problem here. You know, there it was, I think, condition 2, that you should measure under various circumstances, and that problem reappears here in very clear form, namely that you must include all kinds of tests, including, now to have nice examples, the haircut of the experimenter, right? That could be a relevant variable. So please change your haircut and repeat all the experiments that you did for your master's thesis. Okay, it may also depend on the color of your hair. So please, why don't you change the color of your hair to red and then to green and then repeat all the experiments again? And it may depend on the length of your nails. So please cut your nails for the next experiment. And it never ends, right? As I told you, it may depend on the number of chairs in the room next to your lab, right? So put in more chairs, 1, 2, 3, 5. Oh, there are different sorts of chairs. Okay, so, and so on and so forth, right? It may also depend, I mean, the other example here is the position of Venus on the sky, right? Not only the position of Venus in your heart, but the position of Venus on the sky. So you're going to wait a full circle of Venus. Well, Venus isn't too bad because it's fast, but Jupiter is much slower, right? 20 years or something. And for every position of Jupiter, you must repeat your experiment. The y could depend on the position of Jupiter. How do you know? You are dogmatic when you say, of course it does not depend on it. Did you test it? No, you didn't. Okay, so how do you know? So if you really want to be critical, you don't want to be dogmatic, do you? You want to be unbiased. You want to be a critical good scientist. So if anything you state, you must test, submit to test, right? It can be tested. Whether that variable depends on Jupiter's position or not, it can be tested. You just change the position of Jupiter and you could look at your variable and keep the other variables constant. It can be tested. So why don't you do it? Right? You must do it. That's what deductivism tells you. Okay? And that's strange, right? That's not feasible, quite clearly, right? It may also depend on, well, you can continue, whatever you take, right? Everything. Your y can continue on everything. It can continue whether this one looks like that or that, okay? You've got to repeat all your data. All your data of your master's thesis, right? Because it changed this one. And it could depend on it. And you don't know, right? You assume it doesn't. How do you know? You didn't test it. You're dogmatic, okay? That's what deductivism tells you. That's the consequence of deductivism. And that's an unpleasant, what I said, unintended and unpleasant consequence. But it is a consequence of deductivism. And you may get the feeling there is something wrong with it, right? That can't be, in a sense, right? There is something strange, at least, going on here. And that means that a systematic test of the potential dependence of y on u, v, w, and you can take the strangest things, whatever you want, cannot be carried out. Testing cannot even approximately be complete. Never, ever. What you test is, when you really do a test in science, is you single out 1 or 2 or 3 variables or 5, which is a tiny fraction of all the possible variables. It's 0 in comparison to infinity, really. I mean, it's just 5 or a finite number. Whatever you do, there are infinitely many more variables on which the value of the stuff you are measuring could depend. And you cannot exclude it unless you have tested it, that it doesn't depend on it. And therefore, this program of deductivism, especially this critical attitude, which looks so good in the beginning, is something entirely unrealistic, in a sense, right? That's the downside of criticism. It is, once you try to carry it really through and be a consistent critic and say, yes, I will avoid every dogmatism, believe me, then you end up doing the craziest things you can imagine. Yes, you wait for Jupiter to move a little, and then you repeat 5,000 measurements. And then you wait again, right? And someone says, but Venus is much more important. Oh, Venus co-moved, so I got to, and so on, right? And your haircut, and whether you drunk tea in the morning or coffee, and whatnot, and the color of your, and the shape of your hair, and whether you wear a scarf or not, you're going to repeat all the experiments once you take off your scarf. There's no way. You have to do that if you believe deductivism, right? You don't want to do that, so don't believe deductivism. But we should have an argument, right? And that is something we should now develop and look at that a little closer. I tell you now in more abstract terms what that problem is we are dealing with here, because that gives you some insight, also more general insight, in thinking about science, which is, of course, the idea of this class, that you learn to think about science. And in more general terms, the problem consists in the following, that I believe that an account of the development of science must contain the following three elements. You must have an answer to the following three questions, or have the following three elements. You must say something how in science hypotheses are generated, a principle for the generation of hypotheses. You must have a story. Now, I told you already two stories about that, namely the story of inductivism and the story of deductivism. Inductivism tells you, yes, I tell you how hypotheses are generated. You look at the data, right? You collect, without bias, you collect the data, theory-free data, you look at them, and then you generalize under conditions C1 to C3, and then you end up with a nice hypothesis which is inductively supported by the data, right? That's the story inductivism tells you. Deductivism tells you a different story. Deductivism tells you you are free. You are just free in the generation of hypotheses. Do it like Kekulé, but please be so good as Kekulé, then you are successful, right? You can dream up a hypothesis. You are free, right? That's also an answer, right? And a good one in the context of deductivism, because you say, yes, that's wonderful. I'm a creative scientist. I come up with a crazy idea, and then the next step is then that I test it, right? Severely. Well, and that is what I call here a principle for the elimination of hypotheses, right? That is also something you need. If you only create hypotheses, you know, they become more and more and more and more, and not all of them are right and good and usable, right? And useful. So we also need some sort of principle of eliminating them and saying, well, this hypothesis I don't want to keep in science, right? That's also necessary, right? Otherwise, you are overwhelmed by the number of hypotheses because they become more and more and more by this first principle, namely the generation of hypotheses. So the story I told you about the elimination of hypotheses in inductivism was, well, that was condition, I think, 3, that the hypothesis must not contradict any of the data that you collected, right? Then, away with the hypothesis. And the same, well, roughly the same, in deductivism. What you do, you eliminate the hypothesis once you've tested it, and the test was not in agreement, right, within the error bars with the deduction from the hypothesis, right? Then the hypothesis have to go. Okay, so far, no problem. We have stories for that, but here is another principle that you definitively need, and that's a principle for the perhaps only temporary acceptance of hypotheses, in the following sense that you are allowed for temporary stopping tests, not continue testing, and accepting the hypothesis in order to be justified to apply it. Right? Why? Remember, why do we want to have these general hypotheses? Because we need them for prediction, explanation, and technical use. So we must have a point that after the generation of the hypothesis and its justification by empirical tests, however they are done, you may say, now it's enough for the moment, right? And now I can use the hypothesis and predict something or explain something, right? But you must have a stopping point for the testing, right? Someone must tell you it's enough, right? And that is what I call a principle acceptance, perhaps only temporary, perhaps that's not forever, but at least for some time, that allows you to stop testing and saying, it's enough with testing, now I use it, right? I predict something, I explain something, I build something, whatever it is. And you certainly need this principle. If you don't have this principle, then you are stuck with trying to eliminate hypotheses or generate hypotheses. And you never come to what you really want to do with these hypotheses. And there must be a principle that allows you to do what you want to do with them, right? And that's the problem here with deductivism, that it has no principle of the acceptance of hypotheses. There isn't any. It just says, yes, you may accept this as long as it has survived the tests, but at the same time it says, yes, and you must devise immediately the next test. And as I told you before, because a variable can depend on infinitively many different variables, you have no way of stopping the tests with a good argument. There is no argument stopping tests in deductivism. And that's a problem. So you are missing, and therefore I gave you this more general description by which you can apply to any account of science and look, what is the principle for the generation, what's the principle for the elimination of hypotheses, and what's the principle for the acceptance of hypotheses. You need them all. And the problem of deductivism is that it's very weak here, a principle for the acceptance of hypotheses. Because that one overwhelms everything, the principle for the elimination. It tells you science is dynamic, it must continue testing, it must continue testing, it must continue testing, and it must continue testing, right? And it doesn't come to a natural stop. We have an argument to say, okay, forget it now, I did enough tests, I'm fairly sure it's good now, and now I'm going to apply the hypothesis for whatever scientific purpose or extra scientific purpose, but that's unfortunately not possible here. The fundamental problem of deductivism consists in its lack of a principle for the perhaps only temporary acceptance of hypotheses, right? And this is, the criticism goes on and doesn't stop. And in a sense, it destroys itself, right? If you want to be critical, totally critical, you're destroying yourself. That is something that in the Western tradition has not always been seen. And of course, that was the critics of the Western intellectual tradition saw that very often and said, look, that doesn't work. What you try to do is without faith, for instance. It just doesn't work. If you just leave your thinking alone, then you destroy yourself. So you need faith, and here we go, and become religious or whatever. That's possibly not the only answer to that problem. It's one of these answers that have been given in the history of thought in the Western tradition where that problem arises. Deductivism cannot stop testing hypotheses, thus never allowing the move forward to applications, right? And applications, not only technical applications outside of science, but inside of science, right? Science wants to explain, science wants to predict for science sake. But the same holds, of course, for the technical applications, because also there you need a justification why you can stop testing the hypothesis and build a dam, for instance. For the water engineers, right? You need some hypothesis about water and concrete and whatnot and what size, and you need all that stuff, and you need tables, and you want to apply them, right? And someone tested these things, right? These flow equations and pressure dependence of whatnot, right? And at one point you're going to say, yes, it's okay, I've got the table now I build the dam, right? Here's the design of the dam, and it needs this thickness because otherwise it breaks down, and we have earthquakes, okay, make it a little thicker and use more concrete and whatnot, right? But at one point, you start building. Building in the literal sense and in the metaphorical sense, building upon some hypotheses, which you have tested, but you have stopped testing, right? So here is the problem, and so this is very ironic because what makes deductivism so attractive in the first place, right? This idea of being critical and being a scientist meaning being critical. That attractive feature just is self-destructive in a sense, right? It eats itself up. It just destroys itself in a sense. That's very ironic. I can't help it. I didn't create the world. But that is the problem of deductivism, right? You do believe me that I didn't create the world. Thank you. Okay. And the next theory is an answer, as I said, the same way I presented deductivism to you, that deductivism is the answer to the problems of inductivism, And it seemed to be a very good answer and stable answer and wonderful answer that really tells us what science is like. Now we see we run into in a different problem, also already somewhat foreshadowed in inductivism, but really coming to the fore and being very dominant for deductivism in a sense that we must say, unfortunately, that deductivism isn't really a stable position, a position by which you can consistently describe what happens in science. And the abstract description of this failure is simply that it lacks a principle for the acceptance of hypotheses, and people have discussed that problem for decades of trying to supplement deductivism by some sort of stopping the criticism, but that doesn't really work because it becomes inconsistent with the critical stuff. That's the problem. You cannot really improve the position somehow. That's at least so far the experience that has been made in this discussion of deductivism since the 1930s, that it just doesn't work, to modify the position in a way that it becomes consistent and that you get some sort of principle, what I call a principle of acceptance, which allows you to stop testing and go to the next step, namely the application of the hypothesis. This simply doesn't work. And the next position that we are going to discuss is called paradigm theory. You don't know what that means, but I'm going to explain it to you, believe me. And paradigm theory will provide an answer to this problem. But it will start more or less completely anew. We've got to start then, we have to forget everything about inductivism and deductivism because there's a major turn, a turn in perspective. I'm going to explain that to you, what the turn of perspective consists in. And the idea is then that in paradigm theory that we can solve these problems, and also understand what sort of enterprise science is, that it is, of course, somewhat somehow inductive, somewhat somehow deductive, but that's not the end of the story. There's something else in play. That is what paradigm theory tells us. This is paradigms, whatever that is. Okay, that'll be the subject of next session and the session afterwards. Now here a little about the literature. I think I mentioned this book already, Chalmers, What is this thing called science? There you find in chapters 5 to 7 the discussion of deductivism. Right? And also I want to mention this book from Karl Popper, The Logic of Scientific Discovery. That's the second edition from 1968. There are especially chapters 1 and 2. The original was published in German in 1934, if I remember correctly, or 34, now in the 30s. And then it was only translated into English in 1959. Then it became famous, and this is the second edition.